Hello everyone, it's me Raz Mandari and I'm currently studying in the Department of Physics, KIRTIPUR, Kathmandu, Nepal. So I've done my virtual experiment on the topic to study the double slit interference and single slit diffraction of light and to find the wavelength of light. And I've submitted it to the head of the Department of Center Department of Physics, KIRTIPUR, Kathmandu, Nepal. Mm, So I've written here some abstract of my experiment. In physics, interference and diffraction are very important phenomena. So they have a huge application in real world. And this experiment is done to study the interference and diffraction pattern of our light and to study the wavelength of a light. In this experiment, first we observe the bright and dark interference pattern or fringes, and using this, the wavelength of light is calculated. Similarly, we observe the high and low intensity region, that is the diffraction pattern kind of decreasing order, and we found central maxima using these wavelengths of red, green, and violet light are calculated, and these wavelengths are compared with a simulated wavelength. In short, measurement of diffraction and interference patterns are used to determine the wavelength of light. So some of the keywords of my experiment is light, interference, diffraction, and fringes. And I'm presenting an assignment like on the double slit interference and single slit diffraction. In this O, I have tried to give all the important things and information about my experiment. Uh, I've written here some of the main aim of my experiment. So first one is to study the example of interference in light wave. Second one is to understand the interference pattern produced when light passes through a single slit. And third one is to understand the diffraction pattern produced when light passes through a single slit. So if you do this experiment in physical lab, means physically, so we need some operators like traveling microscope, 35 millimeter slide with a single and double slit, and slide holder, and then optical bands, light source, and the screen, obviously. So now the theory of my experiment is when a monochromatic and coherent light passes through a single or double slit, it creates a diffraction pattern on the screen placed behind the slits. So the pattern formed is because of the superposition of wave coming from the slit, that may be a slit of one slit or two slits. So uh, before doing this experiment, we need to know about this figure. This is the interference of circular waves from the two slits. So here we have an example. We have a double slit, and it is called as Young double slit because the experiment were first done by the Youngs, and how light interacts with the light signs through a double slit. At the far end, here we have a screen at a very large distance away from the double slit. The distance between the slits is called the D, is called as a D, and which is very small as compared to the distance from the source had the slit to the screen on the other side. Now what's going to happen is when light shines through a very small opening, that is the very small opening. So when the light shines through a very small opening, light that fracks that the gauge in any kinds of way, let's take an example. If a what happens if a sound wave travels from that opening, and what happens if water wave travels with this opening. So first, and let us take if a sound wave goes through a small opening, then it will bend around the corners and go in all the direction beyond the opening. So if water wave goes through the small opening, it will go all the way around the corner in the different direction, and light waves uh, are no different. When light waves go through the small opening, there were what we call the diffract, bend around the corner and go in all the different direction, which means that the light goes to the top slit with will essentially shines on all of this screen over here, So on the other side, and the light going and the light going to the bottom slit will also shine on the whole screen here on the other side, which means uh, that the light patterns from the both slits will come together everywhere along the slit. But But if we then take a look at the slit, but if we look at the slit, then what will we find is we will see the region where the screen is lighted up and have a bright spot, and then there is a region where we have a dark spot, and it interchanges will go from bright to dark to bright to dark, and on both sides what we call the central maxima spot. So in various and so after this figure of double slit interference, we have a theory for it, and we have a formula to calculate the wavelength of the light, that is the y equals to m lambda L divided by d. From here we can calculate lambda. After that, we need to know about the single slit diffraction. Diffraction pattern formed by a single slit will have a wide and bright pattern at the center with alternate dark and bright fringes with diminishing the intensity on both sides as shown in figure 3. So this figure 2 is single slit diffraction configuration. So before doing the experiment, we also need to know about this figure. So when the light goes through a very small narrow slit, there's also diffraction, and what happens is if we just simply take a single slit light here, the weight of the slit is W. Uh, as light goes through the slit, and if the wavelength of the light are similar in size to the width of the slit, then the energy of the wave will diffract or bend around the opening. Then the wavelength, if the wavelength of the light are similar in size to the width of the slit, then the energy of the waves will diffract or bend around the opening at the slit and go in all the different direction. And what happened then is that the different portion of the beam will begin to interfere one another. Like we have a multiple slit, and the light coming through the multiple slit interferes with one another. Same will happen with different portion of a very same beam going through a portion of going through a single slit. There will be an interference pattern, and because of that an overall diffraction pattern. So the bending of light is called the diffraction, and because of that there will be a mutual interference between the different portion of the beam going to a certain part of the screen over here. And because of that we'll have a high and low intensity. We will have a high and low intensity regions. Notice that the high and low intensity region, notice that diffraction pattern kinds of decreasing intensity. uh, um, the maxima as we go further and further outway from the central maxima becomes smaller and smaller and smaller. So after this figure, we have also the formula y equals to L lambda m divided by W, which is the from which we can calculate the lambda. And this is the figure. This is the photograph of a single slit diffraction pattern on a screen under a red ledger. And after that, we have a figure interference pattern of a double slit showing the overlap single slit diffraction pattern that are the fringes due to double slit interference. And that after that we have observation and calculation of the experiment. So uh, how can we do the experiments? We have the procedure for this. So now we do the experiment like for double slit interference. So for this we have a procedure here. So in procedure, open the simulator. After we opening the simulator, this then wait for 5 seconds for it to load. And then after viewing the wave fronts, these wave fronts, there are spherical wave fronts and tangent wave fronts. So after that, uncheck the box. This is the box for observation. So uncheck this box and so click on show wave fronts. Click on show wave fronts and click on show interference pattern. After the pattern extend to the screen on the full length of the screen, click pause. Click pause here. Then observe the interference pattern. After you observe the interference pattern, click show scale. Then after you have to click on show scale. Uh, then the interference pattern and the scale do not show simultaneously, so the interference pattern will no longer uh, be shown, but the lines of maxima show you the portion of the maxima bright fringes, that is the bright fringes, using the given value of d slit distance. So distance between the two slits, dy on the screen between the central maxima and the first successive maxima, and L the distance to the screen. Calculate the wavelength of light and compare it with the value by the simulator. Repeat using dy equals to y2 minus y1, the second and the first maxima both on the upper side of uh, O, the central maxima. And in step 2, now change the wavelength of the simulator to 500 nanometer and repeat this is step first one as well. So you have to calculate, you have to measure it from the scale. First maxima, first central maxima, second central maxima, uh, uh, this is central maxima, first central maxima, second central maxima. So um, I've calculated the value of wavelength from here, and I've put the distance from the slit to the screen, L equals to 10 micrometer, and distance between the slits is equals to 3 micrometers. So from this, I've calculated the wavelength of the light using the simulated wavelength 400 nanometer. By using the simulated wavelength 400 nanometer, I've calculated the lambda 1 is equals to 420 nanometer and lambda 2 equals to 420 nanometer. So average of these two wavelengths is 420 nanometer, and I have calculated error for these for 400 nanometer simulated wavelength, that is 5%. And now I put the wavelength lambda of a simulated is 500 nanometer. Then by putting the simulated wavelength 500 nanometer, I observed lambda calculated as 540 nanometer on average. So and now we're going to calculate the single we're gonna calculate, we're gonna go for observation of single slit diffraction. So there is a procedure for this. Open the simulator that and in this type opening, click the single slit. Notice that the default color of a light is red, and then chosen wavelength of red is between 635 nanometer to 700 nanometer. Keep all the default values of the slits with W equals to 10 per minus 6 meter and L equals to 1 meter distance to the screen. And then we have calculated it by measuring by measure on the simulated graph the wavelength of central maxima, the dy equals to y1 minus y minus 1 between the first minima on the right and the first minima on the left. Notice that the simulated y is called the x, and also the unit cm needs to be converted to meter. So using the slits with w given by the simulator and L, the distance on the screen, calculate the wavelength and compare with the chosen range of red. And in step 3, you have to repeat the step 2 for a green light, then for violet light. And for green light, the range is 520 to 560 nanometer, and for violet, 400 to 400 nanometer. And you can also observe the value when you decrease the slit width to 10 micrometers. So I've taken the slit width as W equals to 12 micrometer, and distance from the slit to the screen is L is equals to 1 meter. So slit width is 12 micrometer, and distance between the slit is distance to this to the screen is 1 micrometer. So for red light, so I've observed the I observed wavelength for red light on average is 60 nanometers. So from the calculated value of wavelength, we can say that the range of average calculated wavelength of red light is within the given actual range, 635 nanometer to 700 nanometers. So when I calculate the wavelength of the red light, then it is in between the range of red light, that is 635 nanometer to 700 nanometers. So similarly, I calculated for green light. I found 540 nanometer, which is also in the range of 520 to 560 nanometer. And similarly for violet light, I've calculated the wavelength like 450 nanometer, which is also in the range between 400 nanometer to 450 nanometer. And after that, I've decreased the slit width to 10 micrometer, and I've calculated for violet light, the wavelength is 400 nanometer. So it is also in between the range of 400 nanometer to 450 nanometer. On decreasing the slit width to 10 micrometer, wavelength also decreases. So I have result here for the experiment. So hence the double slit interference and single slit diffraction was studied, and wavelength was calculated and compared with the chosen a given wavelength in double slit and compared with the range of wavelength for red, green, and violet, and we got the following results. So what we got from this experiment is, for double slit experiment, when simulated wavelength is 400 nanometer, we get the calculated value of wavelength as 420 nanometer, and error was 5%. And when the wavelength of a simulator is 500 nanometer, we get the calculated value of wavelength is equals to 540 nanometer, and error was 8%. So and for single slit experiment, we get the wavelength of red light is 660 nanometer, for wavelength of green light is 540 nanometer, and wavelength of violet light is 450 nanometer. And wavelength of a violet light, when the slit width is decreased to 10 micrometer, then we get the 400 nanometer, which are in between the range of these red, green, and violet light. So from this experiment, what I have concluded here is it was a wonderful learning experience for me while working on this experiment. This experiment has developed my thinking skill related to interference and diffraction. And in this way, the double slit interference and single slit diffraction is studied and wavelength was calculated. So while doing the experiment, we need to follow the precautions of the experiment. So here are some precautions for the experiment. First one is data should be taken carefully, and second one is experiments should be done many times to get the good results. So also we have the advantage and disadvantage of virtual lab work. So the advantage of virtual lab is student are interested for learning through interactivity and increase the student IT literacy. So though it has also the disadvantage, physical practical skills that are expected of an students are not honed. And I have acknowledgement for the experiment. Primarily, I would like to thank God for being able to complete this virtual lab experiment with success in this ongoing COVID-19 pandemic. And then I would like to express a special thanks of gratitude to our dean, all the teachers, and Department of Physics, as well as the head of the department, who gave me this golden opportunity to do this wonderful experiment on the given topic. So which also helped me in doing a lot of research, and I came to know about so many things. So I'm really thankful to all staffs of the Center Department of Physics, and my parents and my friends as well, for supporting me and for guidance. And I've written here some of the reference for the experiment. After that, I have appendix for the experiment. So what is interference? Interference defined as the phenomenon of superposition of two or more waves of the wave, same frequency emitted by the coherent source, so that the amplitude of the resultant wave is equal to the sum of the amplitude of the individual wave. It is two types: constructive interference and destructive interference. And what is diffraction? The process by which a beam of light is freed out as a result of passing through a narrow aperture or across an edge is called diffraction. And in single slit diffraction experiment, the width of the slit is made double the original width. How does this affect the size and intensity of a central diffraction band? So in single slit diffraction experiment, if the width of the slit is made double, the original width of the slit, then the size of a central diffraction band reduces to half, and the intensity of a central diffraction band increases up to 4 times. And in what way is diffraction from each slit related to the interference pattern in double slit experiment? So the interference pattern in a double slit experiment is modulated by diffraction from each slit. The pattern is the result of interference of a diffracted wave from each slit. And what are fringes? Fringes are bands of contrasting brightness or darkness produced by the diffraction and interference of light with a measurable wavelengths. And what are the essential conditions for diffraction? The essential conditions for diffraction is that the wavelength of light should be comparable to the size of an object. And what is the basic difference between interference and diffraction? Basic difference between interference and diffraction is that interference is the result of interaction of light coming from two separate wavelengths, whereas the diffraction is the result of the light propagation from the distinct part of some same wavefronts. And the fringe width in interference is equal, but a fringe width in case of diffraction is not equal. So in which principle the interference and diffraction is based on? And interference and diffraction phenomena are based on the principle of superposition of wave. And what are the application of interference? So in optical testing, interference is used in testing surface quality like flat surface, spherical surface, roughness of a surface, etc. And whereas in space application includes radio astronomy, measuring light intensity, etc. And what are the application of diffraction in X-ray diffraction studies of crystal and holography? Diffraction is used for this purpose. So I've did my experiment on these.